Thank you for clicking on this Volcano Awareness Month talk. In this presentation, I'm going to summarize many of the deformation signals that we saw on Kīlauea and Mauna Loa volcanoes over the past year. First of all, though, I want to introduce the basic concept of volcano deformation and why do volcanoes deform. The basic scenario starts with magma starting to move into a volcano, much like you can see in this cartoon, magma upwelling into the surrounding rock. This has the effect of pushing on this rock, moving it upwards. And these dots here represent all of our instruments, our GPS instruments, our tiltmeters. Each of those then show motion in the case of GPS, or they show changing ground slope in the case of the tiltmeters. You also start to stress out all the rock around the magma chamber, which creates a zone of earthquakes. Finally, when you reach a stress threshold, an eruption occurs, and at that point, magma moves out of the summit reservoir to feed the eruption, and you see the opposite signal, deflation of those same instruments. So this is the most straightforward scenario. Volcanoes like Kīlauea and Mauna Loa are rarely so straightforward, but nonetheless, in general, inflation shows us that magma is moving into an area, and deflation shows us that magma is moving out of it. Two of the instruments that we use most frequently are GPS, which is shown on the left. In this case, we don't move around with the GPS. Instead, we fix the antenna very firmly into the ground so that we can measure very precisely how that single spot of the volcano is moving. And then on the right is the basic depiction of a tiltmeter. And this long, thin instrument here is the tiltmeter. This bubble level is inside that cylinder, and the cylinder goes down a borehole here. Fundamentally, inside this tiltmeter is a bubble level, not unlike a level that you're used to using in your house, but extremely, extremely sensitive. This is a figure showing GPS velocity vectors from the past year spanning Mauna Loa and Kilauea. So you can see Mauna Loa here on the left with Mokuaweoweo caldera up at the top. Here is Kilauea Summit. This is an old DEM, so there's the old Halema, and then the East Drift is coming off to the east, out here towards the lower East Drift zone. So this is essentially a summary of the deformation that we've seen over the past year, and I'll come back to various parts of this later. I also wanted to introduce interferometric synthetic aperture radar, or InSAR. This is a satellite-based method that gets an image of deformation spanning a wide area. One of the satellites that we use a lot is the European Space Agency's Sentinel-1 satellites, which I believe is what's in the picture there. For InSAR, we need 2 passes of the satellite. So we need it to fly over the ground once, and then fly over again on day 2. And we take the difference in the soundings from those 2 days in order to generate a map of what we call range change. So here, this animation on the right is showing at the top, this is what the deformation might be. So you might have subsidence and uplift, and then at the bottom is the corresponding InSAR image. And so you can see these rainbow patterns, these fringes. This is because the radar wave is an electromagnetic wave with a phase going from 0 to 360 degrees, or 0 to 2 pi radians. And so each of these fringes shows one cycle of this electromagnetic wave. And InSAR can produce images of Hawaii that look like this. So you can see we have coverage over the entire island instead of individual points like we do with GPS or tiltmeters. This is an example of an InSAR image called an interferogram, over Hawaii. This interferogram is from the Sentinel-1 satellite. It's a descending mode orbit, meaning the satellite's flying from north to south. It's looking in this direction towards the west. So the satellite is sending its energy off at an angle towards the west. The first acquisition day was November 14th, 2020, and the second acquisition day was November 21st of 2021, so spanning almost exactly a year. As I said before, these fringes show range change, and range change just means the change in distance between the ground and the satellite. And because the satellite looks at an angle and not straight down, that range change is affected by both horizontal and vertical motion. So what's important about this is that what it means is that sometimes these fringes have patterns that can be non-intuitive to interpret. So the center of the fringes might not necessarily be the center of uplift. And certainly it's not exactly correct to interpret the fringes as just uplift, which can be tempting because they look like topo contours. Another item to be aware of with the interferogram is that it's also sensitive to atmospheric water vapor. And as all of us here in Hawaii know, we have lots of atmospheric water vapor. So one of the reasons why I chose this interferogram was because it was particularly nice, very low atmospheric noise in this interferogram. However, there is still some. So in particular, this band here around Mauna Loa, which is essentially the fog bank that comes, that surrounds that volcano very often. This is the atmospheric effect in the interferogram. There's also a modeled pattern here on the south flank, which is relatively small in this image, but can be a lot worse. This is also turbulent atmosphere that often happens here on the south flank. Likewise, some of these patterns here around Hualalai and on the Kona side and up here on Kahala coast are atmospheric in origin also. So typically, we look for a signal spanning several interferograms taken from different days before saying that any type of a subtle signal is deformation. However, some of the signals are so prominent, it's very clear that they're deformation and not likely atmosphere, as you can see with some of the fringes here along volcanoes. So coming back slightly to this idea of the center of the fringes not necessarily being the center of uplift, I want to zoom in here on Mauna Loa, which is a very good example of this. So this is the motion of Mauna Loa as seen by satellite radar over the past year. Looking at this, you might think that all of the deformation was happening here on the east side. However, if we also bring up GPS vectors from the same time period, we see a much more symmetric deformation pattern. So certainly there is more motion here on the east side, as is typical. This is part of the long-term flank motion on Mauna Loa, but there is deformation on both sides of the volcano. What's happening here is that the horizontal motion away and the uplift, which pulls it towards the satellite, are canceling out to create essentially no range change in this area. So this is an example of how these two types of instruments really complement each other. So we can get sort of a ground truth 3D motion from GPS, whereas the InSAR gives us a full continuous picture of deformation rather than these individual points. So deformation at Mauna Loa has been very modest. There's been very little motion above sort of our background, just a tiny bit of continued inflation. However, it still produced some interesting signals this past year. In particular, a very interesting tilt signal, and the tilt here is this middle box. This upper box is a histogram of seismicity, and this lower box is GPS line length, so change in distance across the caldera essentially a change between two GPS stations. And this tilt signal may not look like much. It's only about 6 radians. But this was a truly unprecedented signal because never before have we seen a tilt signal at Mauna Loa that we could clearly attribute to volcanic processes. So we see lots of motion on the tiltmeters, but they're generally due to seasonal freeze and thaw, pressure changes, daily diurnal heating. We've not yet seen something, not until March, had we seen something that we could very clearly attribute to the volcano itself. And this might be surprising for people who are used to looking at Kilauea, where we see tilt signals all the time, and they're very, very clear and precise. And it really comes down to the depth of the magma chambers. Kilauea has a very shallow magma chamber that makes tilt changes show up very clearly. Mauna Loa's is somewhat deeper, so it doesn't map into tilt quite so readily. So this was kind of exciting just for being unprecedented. However, after this sort of contraction event stopped, Mauna Loa got very quiet. So whatever was going on, whatever it was trying to tell us with this event, it then went very quiet. And then that's how it's been since last March. So now let's move on to Kilauea. And first I'll start out at the very end of the East Rift Zone in the lower East Rift Zone. So first of all, I want to say what it is that I don't see in this pattern. And what I don't see is any indication of magma moving into or moving out of the East Rift in this region. This sort of mottled pattern, all of the hummocky stuff you can see through here, is consistent with cooling of these lava flows. So as they cool, they will subside quite a lot, which is what we're seeing here, especially in this area over Kapoho. We're seeing quite a lot of subsidence. So that's really the only signal that we see in interferogram in this region. And that can be corroborated here with the GPS. So these vectors are all very small, and out of the tip is sort of the smallest. So there's really no indication here of any magma accumulation or magma, moving out of the rift in the lower East Rift Zone. Moving up slightly here to the area around Pu'uo'o. The first thing to notice here is that the rainbow pattern of these fringes, blue, pink, yellow, is the opposite of the rainbow pattern at Mauna Loa, and as you'll see later, the rainbow pattern at Kilauea Summit. This is indicating that this is an area of subsidence rather than uplift. This subsidence only started in December 2020, so about the time that the first summit eruption, sort of post-2018, started. We saw a change from uplift to subsidence. Here's the GPS vector map. It's a little confused. All these vectors are plotting on top of each other, so it's a little hard to see what's going on. Pu'uo'o is about here. But we can look at the time series here of one of these vectors. This is NPOC, which is just to the north of Pu'uo'o. And this time series here of uplift, so this is only the up component of the GPS station, starts right at the end of the 2018 eruption and goes until the end of 2021. So you can see for most of this time period, we saw fairly steady uplift as the rift began to be refilled. But starting just towards the end of 2020, that switched to a very modest deflation, which is what we're seeing now. Moving even slightly more uprift, there's a very curious pattern in between Pu'uo'o and the summit. I won't talk too much about this. However, this signal we attribute to creep, fault creep in the eastern Kauai. Fault creep is a phenomenon where a fault will just slide steadily past itself rather than building up strain and generating an earthquake. So the fault here is just happily slipping slowly every day. This is a signal that we saw prior to 2018, so it's not a new phenomenon, but it is interesting that it continues and that it was quite prominent this past year. It was very, very clearly stuck out in this one-year interferogram. Now, finally, we can come up to Kilauea Summit. We zoom in here, you can see most of the fringes that we see in this one-year interferogram are located here just south of the caldera region. So here's the caldera outline. Here's the outline. This is the portion we call the down-drop block. And then this is now the deeper Halema crater. So most of the deformation in this one-year snapshot is due to an intrusion that occurred in August of 2021 here in the South Caldera region. If you look very closely, you can see some fringes here just circling that down-drop block. That is the deformation pattern associated with deflation during the two eruptions that were spanned by this interferogram. So you can see that compared to this intrusion, those are relatively modest, and it's a very compact spatial extent that is really affected by the eruption deflation. Looking here at the GPS, we see sort of the same thing. So we've got this nice radial pattern. If we kind of look for a midpoint here of this radial pattern, we're actually locating somewhere south of the caldera. So the GPS also, when we look at it in a full year snapshot, it's really being dominated by this South Caldera intrusion. And we can break that down a little bit by station. So first we can look at this station Calm. So Calm is located on that down-drop block. It's as close as possible to the shallow Halema reservoir, sort of as close to being on top of that as we could get it. And so you can see here a very steady increase indicating inflation of that shallow Halema reservoir up until September of this year, when this second summit eruption started, and we saw rapid deflation as that eruption got started. You can contrast that with this Cone Peak station, which is not that far away from Calm. However, Cone Peak is outside of the caldera and out in the South Caldera region. In this case, there was very little motion at Cone Peak. I should say that each of these time series is showing the up-down motion, so vertical motion at each of these sites. So this is uplift and then subsidence. So not much happening here, a little bit of uplift. And then here in August, as this intrusion came through, we saw lots of uplift at Cone Peak, and then slow subsidence. And Cone Peak was far enough away that you don't really see much deformation at all associated with the eruption. And C-Rim, the Caldera Rim Station, which is located just here, that is kind of splits the difference. So you can see here there is some uplift, a little bit of uplift associated with that South Caldera intrusion, and then a little bit of subsidence associated with that eruption. So kind of straddles both worlds. However, none of these stations are that far away from each other. And it gives you a sense for just how spatially heterogeneous the deformation patterns can be. You go from one site to another, it doesn't look like they should be behaving all that differently, but they're showing very different patterns through time. So that that is it for this year's summary. Just to summarize some of the takeaways, I just wanted to present lots of deformation, a lot of the interesting deformation throughout Kīlauea and Mauna Loa. So it's not just at eruption sites, but we see deformation throughout these volcanoes all the time. They're very active in that way. I wanted to emphasize that there's no clear deformation due to magma accumulation in the shallow East Rift Zone, either in the lower or the middle East Rift Zones. Deflation following the eruptions at Kilauea Summit was localized and relatively modest. And then finally, by far the biggest signal that we saw this year was from this intrusion into the South Caldera region in August. Part of the reason for that is what we're measuring with deformation is storage. If the magma is trapped and creating pressure in the magma chamber, that's when we see deformation. So in a sense, that intrusion where nothing was erupted, really just pressurized that region and produced this nice big deformation signal. So of course, this was a talk all about deformation, and at this point, you may have seen the other Volcano Awareness Month talks on different data types and different disciplines. And I want to emphasize that we take all of these data together. We never look at one data type in isolation. So in order to gain a complete picture of all the phenomenon that I've talked about today, we really look at all of these data together and bring together the perspectives of all the different scientists at the observatory. All right, thank you.